I think we'll go ahead and get started. Welcome everyone, and thanks very much for coming to this special seminar. It is with great pleasure. Hi, John.
Hello, sir. How are you doing?
More people to come in?
Yes.
And GIWS is an associate professor in the Department of Civil and Environmental Engineering at the University of Waterloo. He is a Canada researcher in hydrologic modeling and analysis. Jeff is an awarded university professor, and James, yeah, just to name a few, he's a recipient of University of Waterloo Outstanding Performance Award, Stanford Fleming Foundation Teaching Excellence Award, UW Faculty of Engineering Distinguished Performance Award, and probably early on in his career, an Early Researcher Award. He is, as many of you know, he is the lead developer of Raven, that is a hydrologic modeling toolkit. And he's also leading the lead person of a GWF-funded project, Northern Water Futures. And he's really here as part of his visit to explore synergies between that project and INPC project that is based at GIWS. I've known him for almost 10 years, since the first day that I arrived at Waterloo as a fresh PhD student. I guess back then you were a fairly new faculty member, and I remember his office tour was always open to students, and I bugged him a lot myself, and he was always there to help mentor new students, and thanks for that, James. So he's going to be talking about a major issue in hydrology, upscaling or scaling issue in hydrology, and I'm looking forward to it. At the morning we began a very nice conversation about these issues, and I'm hoping we'll continue the conversation in the next, or today and tomorrow basically. So if you wanted to meet him offline, you can talk to me or Amin, and we can set a time for you guys to meet. Thanks, Jeff. Thanks, James. Yeah.
All right. Thanks, Aman. So I'm going to preface this talk by noting that I have not found the Holy Grail. This is the search for it. The goal of my talk today, I'm going to be talking about upscaling in computational hydrology, and what I'm really looking at doing is trying to take our understanding about how hydrologic systems work at the point scale, where we actually have a very good understanding of how these systems work, and take that information and scale it up to large scales, watershed scale systems. I'm going to be giving I'm going to spend quite a bit of time as an overview of what's been done in the past, kind of get everyone up to speed in terms of how do we think about upscaling, what upscaling works, what doesn't work. I'm probably going to provide some opinions along the way of what constitutes smart upscaling or pragmatic upscaling. I'm going to talk quite a bit about this issue of pragmatic upscaling versus highly theoretical but pretty much useless upscaling. And then I'm going to talk about a few processes, a few approaches towards upscaling that I think can be promising moving forward. Again, moving towards capturing this Holy Grail. All right, so as a first premise, I want to talk about what this thing called upscaling is. The basic premise here is that over the last 150 years, we've spent a good deal of time looking at the very detailed movement of energy and soil moisture and water across our landscape at the point scale. We've got, relative to the watershed scale, these things are easy to instrument and characterize. People can build soil columns and look at very details and characterize these things at very small scales and measure all of the quantities involved and understand them. And from that, these tests over the last 150 years, people have developed rules, guiding principles for how these systems at the small scale work. So we can express mass balance, momentum balance, energy conservation. It can express all of these things at the small scale. We end up with things like Richter's equation in the unsaturated subsurface, overland flow equations, mass energy balance in a snowpack. We can describe these in a great deal of detail at what I'm calling the microscale, the representative elementary volume scale. We're still not perfect, but because these are things that are measurable, we can actually focus in and zoom in at the small scale. We have a much better understanding. Then we know the rules generally at these small scales. And because of this, we can develop models of this microscale. If we know the system, we can parameterize it, we can apply known forcings, known shortwave radiation, et cetera, we can build models that perform well without calibration, because these are systems that are, we can actually understand them enough and characterize them well enough to simulate them. Once we move up in scale to the watershed scale, so we move up to 10 square kilometers, 100 square kilometers, 1,000 square kilometers, the rules change. Richard's equation is valid at that point scale. At the larger scale, perhaps not so much. We have an observational problem at the watershed scale. There's only a few things that we can observe that are scale appropriate at that, such as stream flow. So stream flow is an integrated observation. It's telling us about the functioning of the watershed as a whole. That is something that is an observation that characterizes the watershed. However, there's very few observations that we have like that. Aside from a hydrograph, we can't go out and build something like a 10 square kilometer lysimeter. Well, maybe now we can with GWF. I think that's a worthwhile endeavor. But there are still some things we can measure via remote sensing, but it's still a very incomplete observational picture of an entire watershed. We can send out LiDAR right now and get a good deal of information about what's the surface processes, but as soon as we go 2 inches below the ground surface, observation doesn't, large scale observations we don't have. We also don't have an ability to characterize these systems. We can't send out an army of thousands of co-op students to take soil samples and measure hydraulic conductivity and characterize all the details inherent in a heterogeneous watershed system. So part of our problem is in characterizing the system and being able to observe at those scales. The other problem we have is that the rules change. When we move from the microscale to the mesoscale to the macroscale, we are no longer dealing with the same rules. Things like Richard's equation, which is valid in a small parcel or inside of a soil column, at the macro scale, these are simply useful approximations of what the upscaled behavior, the upscaled rules of the system might look like. So this changing of the rules is the fundamental issue which I'm going to talk about today. So upscaling. Upscaling refers to this process of trying to take information, that understanding of what happens in details at the fine scale, which we know reasonably well, and figure out how do we determine what the rules are at the bulk scale. So we want relationships between things like bulk soil moisture and bulk fluxes in our system. We might have to bring over some information about the distribution of those properties on the landscape, but we still want to be able to characterize them in bulk at large scale. So ideally, so we're talking about taking a system like this. This is in this case, I'm just treating it as a two-dimensional system. We want to express the flux through this plane here. Right, so this is our macro scale system. We have the flux, so we can describe this at the point scale. So this is a single vertical continuum. We've got canopy, snow, ponded water, soil continuum, some groundwater in between. And we can characterize at the point scale at a single location. We can characterize the flux as a function of parameters in the system. So this is a vector of parameters and a vector of states in the system. And that is our constitutive laws that govern flow of water, or this could also be energy fluxes in this system. When we move to the macro scale, and this could even just be a 50 by 50 square meter plot of land, we now have a heterogeneous system. It's laterally heterogeneous, it's variable in the vertical, and now we're talking about trying to get the mean flux through this plane as a function of the distribution of parameters in space, distribution of states in space, so moisture content, temperature, etc. And we want to boil this down to a new constitutive relationship, which is in terms of the bulk properties of the medium and some bulk parameters which define how those fluxes behave. And this is the end goal of upscaling. We want to end up with new constitutive equations that describe the bulk behavior as a function of the bulk properties that may or may not be measurable, and perhaps including some information, we may have to include some information about the distribution of those properties internally. This leads to new constitutive equations, and in some cases it will also lead to new conservation laws that are different rules. We're going to have different rules at different scales. And that is the upscaling process. To provide some context for this, so this can be a very complicated process. If we go through and try to build this up from first principles, we may run into a lot of problems. In fact, people who have started up from first principles run into a lot of problems with the math really fast. However, I don't believe that that's entirely necessary. And the context of that is the particularity of hydrology as a whole, in that it's a simplifying process generally. So right now, for the last 70 years, we have not had these rules for the mesoscale and the macro scale. We don't know what they are yet. We're still working on that process. We don't have a comprehensive upscale description of the system. However, we can build models that still do a pretty reasonably good job, even with calibrated conceptual models. So why can we do that? Why can we get away with that? And the reason I think this is the case is because the scaling of processes in watershed systems, it's a simplifying process rather than one that makes the system more complicated. If you're not familiar with the butterfly effect is this concept that a butterfly flapping its wings in China can create minor turbulence, which then, through a sequence of nonlinear processes, can become a hurricane. And it's this concept that systems can have very high sensitivity to initial conditions, which propagate through a nonlinear system that can have massive effects. Hydrology, in many cases, is the opposite. Those little details get smeared out, damped down. Small differences in initial conditions get petered out. Local phenomenon are often only local, and they stay local. Watershed memories tend to be short. Again, not in all cases. This is why we treat watersheds as quasi-steady state. Every year they reboot. That's why we have a water year. Every October we can reboot our model. And the idea behind smart upscaling, I think, should be this process of figuring out why is the watershed simplifying this process? What about this watershed allows us to get rid of all these redundancies, as is implicitly done in the development and deployment of conceptual models, and except in those cases we don't know what's happening internally. We'd like to be able to get that from first principles by explicitly tracking through and figuring out where is the redundant information, when can we throw it out, and how. So here's our fundamental problem of upscaling. We want to be able to figure out how do we determine scale-appropriate constitutive relationships such that we have relationships between flux and storage that do two things. Appropriate pragmatic upscaling should respect two concepts. One of which is that we want them to be theoretically sound. We want the models at the large scale to respect the natural heterogeneity at the subgrid scale, the important natural heterogeneity at the subgrid scale. And we want them to be consistent with the physics, such that if we took that model and kept zooming in on a smaller and smaller parcel, eventually it would then return to the Discharge equation or whatever our point scale model is. This would be the ideal scenario for an upscaling approach. The other thing, I'm an engineer and I'm a guy who likes to simplify things. We also want it to be usable. And a lot of the problem with stochastic theories and the mathematical techniques that people have deployed for uncertainty, for upscaling of heterogeneous systems are immensely complex, and I'll show you an example of this. And they work under a variety of assumptions which are never valid, and therefore they're not very pragmatic. So then how do we figure out upscaling approaches that are not only theoretically appropriate, but pragmatic? And then, okay, why do we want to do this at all? We could get away with taking every watershed and breaking it up into 10 to the 9th little blocks and solving Rich's equation and overland flow equation and all those other things on each and every one of those blocks. And there are colleagues who would advocate for such approaches, but you don't learn anything from these brute force simulations other than how to burn a supercomputer down to the ground. All right, so we want to do things that ideally will provide insight into why the system simplifies itself. We want to identify emergent behavior. So emergent behavior, if we look at the air in this room, we've got beyond trillions, many little molecules that if we want, we could track pressure differentials and all this by tracking the progress and process of each one of those particles in the room. But we don't need to define those 10 to the 29th particles in this room in order to apply the ideal gas law. The complexity at the microscale all kind of goes away, and for most practical applications, we can apply PV equals nRT. That's an emergent behavior that we could not derive directly from all those infinite number of molecules. So we want to identify what are the causes of that emergent behavior. We want to remove redundancy in our description of the world. We'd like to not have to parameterize every single detail of the globe. And ideally, if you do this right, we'll get more scale-appropriate models that can be used in practical situations. I mentioned in the title of this talk that this is a holy grail, and the basic concept behind a holy grail is that it is a quest that you will probably not be able to achieve. And so this was laid out by Keith Bevan in a 2006 paper, who basically said this hunt for scale-appropriate closure relationships should be considered a holy grail for hydrology. It's worth going on the journey even if we can't get to the end. And that's what I'm talking about today, is this journey. There's an extensive amount of literature on the topic of upscaling. This is a handful of scores and scores of useful and interesting papers. The approach is actually pretty sophisticated in the groundwater literature, and the reason for this is because we can take a parcel of groundwater and imagine it extends out in infinite directions, and there's no influence of boundary conditions, and there's no influence of interfaces, and we can treat that as a statistical description that extends out in all directions. And once you do that, you can do some very neat things mathematically to get closure relationships at large scales. In surface water, that's less the case because interface conditions, the geometry of the topography, it all influences things, and we can't have an infinite domain such as we can in groundwater. But we can borrow some tools from that. The practical implication of all these approaches, despite spending our time since the late 1970s, the practical implication of these approaches has been pretty limited. All right, history of upscaling approaches. When you go through the literature, I'm going to map the range of approaches on two axes. One of these axes is theoretical rigor. So that is, how well do these approaches actually respect the microscale physics? How much of the detail of probability distributions and covariances do they include? And then I'm going to put them on another scale here from simplicity, so tools that provide insight, that are pragmatic to use in practice, to complexity. The laziest version of this, we can build a not so theoretically rigorous in terms of upscaling. We can just build a giant model with all the details included and use brute force over the discretization. We have a huge complex model that provides very little insight necessarily into the system. Most of the tools are going to end up on this diagonal. The simpler models are going to be less theoretically rigorous. The more complicated models are going to be more theoretically rigorous models are going to be more computationally demanding, more mathematically demanding. And there's a range of tools from hydrograph fitting. This is a form of upscaling. We're inferring from the hydrograph using box models that are conceptual descriptions of the landscape. We're inferring from the hydrograph what the bulk behavior of the system is. So this is regression of various regression methods for fitting base flow coefficients, for example. There's a variety of techniques which use and respect spatial variability, so they use the snow cover depletion curves, a variety of other technical methods that say, we recognize there's subgrid scale variability, but their conceptual model might not be consistent with the microscale. And then there's some very complicated mathematical approaches which, from first principles, start with Richard's equation, deploy a whole bunch of averaging tools, and end up with almost impossible equations to solve. So they get here, and then they immediately have to backtrack to here to make it a solvable mathematical problem. What I'm looking at is, can we get into a sweet spot over here where our models are relatively simple and theoretically rigorous, although they don't require all the details about the microscale to be useful. So this is really what I'm aiming at. This is that pragmatic upscaling region. All right. Some water. So basic process of upscaling, just to go through a few details here. I just want everyone to kind of, again, be on the same page. Here is a heterogeneous domain. We're just going to look at a simple infiltration process. So this is a system where we have maybe different porosity, different hydraulic conductivity of all these different panels, and this is what introduces the heterogeneity. This can be described as we have a state vector here in terms of moisture content distributed along this landscape, a function of space and time. Parameters distributed across the landscape in terms of space and time. And we can solve the problem of infiltration in each and every one of these heterogeneous parcels and get a flux as a function of space and time. In upscaling, what we want to do is we want to take this complex heterogeneous system and somehow describe its bulk performance, that mean flux, mean infiltration, based upon at least the mean soil moisture and mean parameters that describe the bulk system, and perhaps some information about the correlation structure, both spatially and temporally, between the parameters and the states in the system. So that's our goal of upscaling, is taking some of that subgrid scale information and be able to use it to estimate fluxes at these larger scales. There's many approaches for doing this. The easiest and laziest approach for doing this, so we have our microscale flux. Our flux is a function of parameters, vector of parameters, vector of states. We can average directly. We can solve this problem 1,000 times. We get the flux at each one of those grid cells. This is the local flux. We scale it up by the area. That gives us our average flux. This doesn't help us because we still have to solve the problem on each and every grid cell, right? So that is the bulk brute force approach. So we can also treat this as, this is equivalent to integrating over the domain. Again, not directly useful because we need to know all of the details in order to get the bulk flux. So that is really not upscaling at all. This is just averaging to get our flux. This kind of approach, it's useful for independent vertical processes. The tricky part is the evaluation with integrals. Generally, we need to know what are the parameters everywhere in space, what are the states everywhere in space, or we may be able to get away with describing these as a probability distribution of the parameters, probability distribution of the states. Oh, thank you. So, again, this is area averaging. This is the simplest form of upscaling problem that mentioned to basically a zero-dimensional problem. How do we do that? Laziest thing, we say our parameters, we're just going to replace that with the average parameter. Our states, we're going to replace that with the average state. And therefore, this is easy. We now replace that integration process with just treating this as an equivalent homogeneous medium. It throws about any of the information about the variability, assumes we have zero variation in the parameters, and it's generally wrong. So, next step we can go to is the process of effective parameters. We're going to say that this is not right because it ignores all of the interesting stuff in the middle. So next step, we go with effective parameters. And this is what most calibrated, physically based models are doing. They're applying Richard's equation over a 100 meter by 100 meter parcel in a heterogeneous landscape. And they're saying, we're going to calibrate this model such that the saturated hydraulic conductivity is an effective one for the whole domain. So we're replacing our spatially variable properties with a single property, and we're saying that our spatially variable soil moisture, that variability can be ignored, and we end up with, again, a simple problem. We've replaced the average bulk behavior with the point scale behavior, which again is not correct. It neglects any of the artifacts that can come from scaling, and there are quite a few. I'll show some examples of that. It assumes the constitutive law is the same at the large scale as at the microscale, which again is typically wrong. But this is the approach that we typically get with calibration of mesoscale models. So, how do we start to respect this? Well, more sophisticated approaches instead say we're going to do things like, we're going to respect the fact there's a variation internally, but we're not going to explicitly represent the spatial correlation. So we replace this distribution with a distribution of parameters, like hydraulic conductivity, and then we try to solve a slightly different problem. Instead of integrating over an area, we're now talking about integrating over a probability distribution, and we can do things like Monte Carlo. This is the hard way to do it, which basically is also just the brute force problem. But there's ways to analytically solve that Monte Carlo problem, and this is called the derived distribution approach. approach. So instead of solving this on 10,000 squares, we can solve this problem in closed form in terms of probability distribution to the fluxes. And this is one of the approaches I'll talk about a little bit today. Again, I said I was going to spend some time on the background here, again, to get everyone up to speed. So, areal averaging primer. So this is a simple relationship. We have some single microscale parameter, a single microscale flux. We have a relationship between the state and the flux. We're going to fix the state and calculate the flux here. This could be a relationship between soil saturation and infiltration. So, homogeneous domain, we put one parameter through this state flux relationship, we get a single parameter, single flux out. It's a fictional homogeneous system. Often in practice, what we do is we try to break up the world into some parcels, and we can solve this in subsets of the domain that are sufficiently different, and we're going to get 3 different fluxes for each of these 3 domains. So discretization partially alleviates this upscaling, these upscaling issues. And then we have our heterogeneous domain. We describe our parameter by a distribution. We can then map this distribution through the function, and that's going to give us a distribution of fluxes. The key thing here, and this is the reason why effective parameters don't work, is that the mean flux that we get from mapping this distribution through here is not the same as taking the mean parameter and mapping it directly through the function. So this is the key reason why effective parameters don't work. This equivalency is not valid unless you have a linear process. That's the only time when you can get away with this. With a linear process, this is allowed, and we can directly upscale. And how many of our processes are linear in hydrology? A few. We can sometimes get away with it, but not always. Of course, this is the 1D case. This is actually a higher dimension problem. So we now have dependence upon parameter and state, giving us a distribution and the mean, and you add multiple parameters, multiple states. All of a sudden, you have that mean behavior is very different from the behavior you get by putting in all the means into your expressions. So that multidimensionality basically throws out even this utility, because most problems are multidimensional problems. All right, so key point, upscale behavior functionally different from local behavior. This is that emergence of new behavior from looking at a heterogeneous system and how the heterogeneous system behaves. There's different rules than the homogeneous system. So we can always get around this by over-discretization. Parameterization is still a huge problem. We can't characterize the world in that level of detail, and we don't learn much from it. We can always build a massive model, run 100 times, many parameter realizations. What do we learn about controlling factors? What do we learn about, what insight do we get into that upscaling process? Not a whole lot. I'm interested in trying to identify these scale-appropriate models and evaluate things like parameter uncertainty there. If we don't know the landscape, I'd rather use the simpler model to assess uncertainty than the sophisticated model to assess uncertainty, which you can run twice because it takes 3 weeks to run. All right, so emergent behavior. Here's a very simple example of where emergent behavior arrives. So this is a paper from 2010 that I worked on. We can develop, this is infiltration process. Everyone who's taken a hydrology class, you have an initial saturation in a porous media. We apply water, a constant rate of water on top. We have the ground saturates, it hits full saturation, and then a pulse of water moves down into the subsurface. And we can plot this in a uniform 1D case as basically being in a constant infiltration rate until we saturate the ground surface, and then our flux in through that ground surface is going to deplete over time. Everything beneath this curve effectively ends up as infiltrating. Everything above this curve effectively ends up running off. So that's classic green-amped problem. And if we can solve this analytically, applying a PDF of saturated hydraulic conductivities. And as you increase variance, you're basically averaging a whole bunch of these curves over all the parcels. And the average of a whole bunch of these curves with a sharp time of ponding is something that has no sharp time of ponding and a functionally very different behavior. This is a high variance case here. The dots here are Monte Carlo compared to the analytical solution here. And the shape of this curve could not be described with an equivalent one-dimensional medium. So we can't just replace the heterogeneous problem with a green AF problem because it's not. And this is a very simple case where the emergent behavior is functionally different. This has the same mean hydraulic conductivity, so we can't use the mean hydraulic conductivity, and we can't use an effective one either. Because an effective hydraulic conductivity would have some period of time where all the water infiltrated, and that's not seen. And this is common. This is the simplest case. So emergent behavior, these effective parameters generally not really valid. And again, this is the 1D case. This is the easy part. We can treat these processes as independent. We can map things through into a probability distribution. Once you get to 2D and 3D and processes where there's lateral flow and there's dependence upon path of the water through the system, this gets even nastier, and our governing laws become even more useless. So if you go through the mathematical formulas for upscaling these directly, they're ugly, ugly, ugly. So let's talk about some higher dimensional upscaling approaches. So other approaches start from fundamentals. We start with Richard's equation, we start with the detailed system, and then we average them. And we carry with it all the covariance and the structural correlation and all those details in that averaging process. This is very general, but it is very hard to do. So this is the dominant approach to using groundwater, from Gelhard and Axness all the way up into recently. This is the suite of, for those, there's a number of perturbation approaches, some very nasty phase space approaches which create new governing equations which are mathematically super difficult to solve. And we end up with upscale problems which are more difficult than brute force and more difficult than solving the original microscale problem. We got all sorts of issues here with solving things in that way. So here's an example. Here's two ordinary differential equations describing temperature of snowpack and depth of snowpack at a single point. This is one formulation, and for a single layer snowpack, we can solve these no problem. Let's solve it for a heterogeneous domain with heterogeneous radiation where there is correlations and covariances that we have to track through between temperature and depth and consolidation and some dependence here on density and whatnot. And you do this once, the right way, and look at what we get. I don't know how to solve this. They didn't really know how to solve this either, incidentally. We carry with us all these covariances of the right-hand sides of those differential equations. Everything's dependent upon the complete integral of those covariances from the initial state to a year later, and how practical is this? Not very. So if we want to do this right, we're going to have to be a bit more clever. So this is the standard approach used in the pretty generalizable approach that's used. We start with our microscale equations. We break our problem into a mean state variable plus a deviation of state variables. This gives us two sets of equations. Spatially averaged equations, so the Richards equation in terms of the average moisture content, let's say, that carries with it the deviation from that. We end up with another equation for deviation that carries with it the mean. So this, to solve this, you need this. To solve this, you need this. We've now just made our problem harder. No simplification involved. We need to make a number of assumptions in order to get rid of this effectively. Get rid of all the details that are internal. And so these are assumptions of ergodicity, statistical homogeneity, small variances, etc. And that allows us to get rid of redundant information and end up with spatially averaged equations. Sometimes we can do this, sometimes we can't. But this is the basic approach towards smart upscaling convergent principles. It's still pretty hard, and still not necessarily always practical. So on the flip side here, there's a number of things that are all over the place in hydrology which are implicitly upscaling approaches that retain that information about microscale variability. And they have mixed degrees of respect for first principles. One of those things is snow cover depletion curves. What is this trying to do? It's trying to respect the fact that we can't describe a snowpack and the melt of that snowpack using the mean snowpack, snow depth alone. we need to know something about the distribution. Specifically, we need to know what percentage of the land cover is covered by snow. That is a very simplified, low-order upscaling technique, trying to retain and respect and integrate subscale variability. Unit hydrographs. This is a probability distribution of travel times through the landscape. We try to respect the fact that there is that all the water doesn't show up at once. It shows up with various lag times across the landscape. Box models. A number of things like the probability distributed model, the Vic model, top model, and variants that use topographic index. They're using, again, mixed degrees of respect for first principles, but they're trying to respect the fact that there's spatial heterogeneity in the system and directly include that in the model. So this is coming back here. We've looked at these. These are those simpler ad hoc approaches. These are those complicated approaches that bring with them a lot of mathematical baggage. Now let's go back to the sweet spot. I'm interested in pragmatic upscaling. So can we find things that generally respect, can we solve these problems in a way that generally respect the subgrid scale of physics? That we have a simplification involved, that we usefully simplify the problem, reducing the amount of detail we need to solve the problem. And this is because upscaling, as we see, without simplification is not valuable at all. And we want to be explicit in our assumptions. I want to understand, why can we get away with a power law description of infiltration in Sacramento model and all these things? There's a reason why they're getting away with it. There's a reason why the system scales in that way. What is it? Let's find out what those assumptions are that are required to get you from the micro scale to the macro scale. And I'm trying to spend some time looking at lateral flow because that's a particularly thorny problem in these upscaling approaches. So I'm going to go through, let's check my time here. Now I'm very near the end here, but again, it takes you a while to get to the stuff, and hopefully this makes you think a little bit about the upscaling process as a whole. We're talking about two approaches that we've implemented recently, one of which is the derived distribution approach, which is analytically calculating PDFs through relationships. These gives us simple but models that respect the subgrid scale detail in closed form. I'm going to talk about data mining approaches. So this is a site in the Northwest Territories. This is the Scotty Creek site, and recently people in the field have noted that this is a sequence of bog cascades. There's thousands of these bogs, and generally they're isolated, they're not connected to the fen system, and then when there's a big snowmelt event or rainfall event, these things start to connect. So this one will fill up, it'll overflow into this, will overflow into this, and they'll cascade into the fens, and then what was not connected previously then connects. And we can conceptualize this as these bog cascades. Each of the bogs has a contributing area. Once this fills up, it overflows to here. This has a contributing area and overflows. And we can treat this in a pretty simplified manner. So this is a runoff area to fill up the deficit and then overflow. Fill up the deficit, overflow, etc. Now this is a very simple local model. We can't represent this system of tens of thousands of bogs using a single 3-bog cascade, because it just wouldn't work. It would be completely, we'd have to fill up that one deficit before we saw any flow from the outlet, even though half of these may be overflowing and half of them might not be overflowing. So we can't just directly apply this using a local scale model to get the emergent response of the system. But we can take an extremely simple box model of the system. So if we ignore temporal variability, we can look at our potential outflow is what comes in. Once we fill up our deficit, we get outflow. I'm not going to get into the mathematical details, I don't have the time here. And then in downstream bogs, we also have to address the fact that we may or may not be getting water from upstream, and we can propagate this through. It's a very simple model. You can code it up in Excel in 5 minutes maybe. Math. The key thing I want to impose upon you is that we can analytically, if we know the distributions of the bog contributing areas, if we know the distributions of our deficits or have some estimates of what those might be, we can propagate those distributions and solve the Monte Carlo problem exactly for a 10,000 or 100,000 bog system. And for a single bog cascade, we can get very simple relationships So this is analytically tractable. We can solve this and code this up very readily. Where we end up with our, given a certain precipitation event, we can calculate the mean output from that event based upon the amount of the size of the contributing areas of each one of those bogs and the size of the deficit. So in this case, if we have, so for example, it's going to take some time. We need a minimum precipitation event to fill up enough of the bogs to have outflow generated. And then as the precipitation event increases in magnitude, more and more of those bogs are filling up and then cascading and overflowing, leading to more outflow from the basin. And so that's for a one bog system. Similarly, this is going to change with the distribution of the contributing areas for each one of those bogs. We can solve that analytically. We can actually also do this for a two bog sequence. And this is just a distribution. This is the deficit distribution. So this is our initial deficit distribution. So all of them have about 30 millimeters of fill-up space before any of them will outflow, and then some of them have maybe 200 millimeters of fill-up space before the outflow. And then as you add water, more and more of these are going to cascade, and then you add a lot of water, most of these are going to be filled and outflowing, but you're still going to have some percentage that still are running a deficit because they have to be filled even further. So this is an example of ways we can propagate through a simple model that probability distribution in a system with lateral flow, which is usually not an easy thing to do. And we can do this for 3 bogs and 4 bogs and 5 bogs, and I think around 5 is where the math becomes too gnarly for me to digest. I haven't quite gotten there yet. Why were we able to do this? There's limited depth of information transfer. We're ignoring transients. But the nice thing is this is analytically tractable. We're respecting the local scale that we really can't characterize that well except with probability distributions. And then we end up with a 3-parameter model in the end for a large expanse of a complicated system. Where we might have just inferred that from the hydrograph, and we get something like this is treated using SCS curve number, but not for the right reasons. Now we actually have a justification for why this shape is useful, because we propagated it through the local model. All right. The other approach that we can look at is the data mining approach. And the basic approach for data mining is we have models, we can build these complex models, large-scale models with all the microphysics included. So we can build a hydrogeosphere model with 10 to the 6th nodes and Rich's equation, groundwater flow, all that stuff. We can build these models, and we can build a hypothetical toolbox, and we have complete control of all the parameters. So we can try to learn about how systems upscale by monitoring 3 or 4 watersheds, or we could monitor 10,000 hypothetical watersheds to look at what are the controls on upscaling. So we can take those models, run them through under a variety of conditions, variety of topographies, variety of soil heterogeneity, focusing in on one of these things, and we can calculate those mean low order moments of state variables and fluxes and try to infer the constitutive relationships through regression. And so this was used for unsaturated flow in the past and also for lateral groundwater flow, base flow from systems, and I'll be talking about that. The benefits of this is that we have complete control over our system. We can test hypotheses about what leads to successful upscaling and what does not. And we can explicitly test the range of possible options. The detriments is that it's possible upscaling relationships won't exist. We're probably going to have things that are systems that are hysteretic, and we're going to have to somehow be very careful about how we characterize that hysteretic behavior. But it is one mechanism by which we can infer these upscaled constitutive laws. Of a data mining approach. So very simplified explanation. This is ground surface. We can apply different recharge levels and look at a steady state water table under each one of those recharge conditions. Right? So we have a recharge flux, different average heads in this system, and we're going to have different average fluxes through this surface water and this surface water release here. And these are going to turn on at different times. So we took a hummocky terrain. This is the normalized hydraulic head for a low recharge case, moderate recharge case, high recharge case. So this is basically looking at all those various different states look at the head distribution. We can look at the ET distribution as well, groundwater ET. As we raise the water table, higher recharge cases are going to have a higher water table, more water is going to evaporate to the atmosphere. We can look at the discharge, so all the points at which water is draining into a surface water feature or discharging as the spring. Low recharge, moderate recharge, high recharge. The higher the water table gets, the more opportunities the groundwater has to exit the system. And then we can also look at the saturated area fraction as a function of mean head. So we ran this through a relatively simple model initially with different terrains. So this is just an example of one terrain where we tracked, added recharge, steady state conditions, determined the head, and we got these relationships between ET and normalized head under a variety of conditions. So this is under a number of different hydraulic conductivities. Again, initially homogeneous. This also includes heterogeneous hydraulic conductivity. What was the other thing that was modified here? I forgot here. Various PET rates, and they were unnormalized PET rates, and we all collapsed along this same curve. This is that natural simplification of the system that's leading to a power law relationship. Again, one of these curious things, why are these conceptual models working so well? They're accidentally upscaling physical processes that they're inferring from looking at the hydrograph. And this is what would be done, this is what we would get if we just naively upscaled the point scale process. This would be our ET trend. It's not right. Likewise here with discharge, there is no naive upscaling of discharge because the discharge doesn't present itself until the water emerges from the ground surface. So if you treat it as an equivalent average elevation surface and then the water table hit that, then you can't even calculate the steady state discharge. It doesn't make any sense. But again, you collapse all along the same curve, collapse all along the same curve. And this is inferring from the microscale model. This is a lateral flow process, and we back out the emergent behavior. Now, there's still some missing parts here. The nice thing is, we tried this, we did this also with a hydrogeosphere model that included unsaturated zone transients, and it still worked, which was very surprising to us. Now, we don't have the direct causation. We can't directly map the topography parameters to those power law coefficients, but the interesting part here is that those power laws emerged as the bulk behavior from solving the groundwater flow equation in these systems. And again, this is one of those possible justifications for why can we get away with these use of the conceptual models. All right. Actually doing pretty well on time here. So, some thoughts on upscaling. Not everything can be upscaled. Certain phenomenon you're going to need to know the detail, the microscale detail. If you have a sequence of lakes draining into each other, we can end up with a single lake that will not overflow, and you need to know information about that detailed lake, about when that lake overflows to understand how the whole system behaves. And this, so we need to know the details in order to know the bulk behavior. This is, of course, in some cases we can avoid knowing the details. Averaging alone does not simplify the process description because to average, we need to know the details about what's happening internally. What simplifies is the assumptions we use to throw out the redundant information. Averaging in and of itself is not useful to us. Upscaling lateral processes inherently more challenging, which is why we have to turn to some of these tricks that I showed here with the data mining and whatnot. And this is further complicated by things like internal boundaries and structure, which sometimes you can ignore in the groundwater upscaling, but not when you talk about surface water systems. To conclude, understanding the upscaling process is desirable. We want to be able to figure out what happens between the point observation and the stream gauge. What are all the processes that are leading to that inherent simplification? We want to be able to avoid the required application of brute force. I'm not a guy who likes brute force. I'm a simplifier, and so I want to understand what's the smartest way to simplify. Upscaling should be a simplifying process. Ideally, it should help provide insight into how the system functions. A lot of tools in the literature right now, while theoretically rigorous, super clever. They're really cool mathematics, Fokker-Planck's equations, phase space probability and phase space, crazy things. They're not very useful. And so I'm interested, and I think we need to refocus in the research community as a whole into pragmatic upscaling that gets us, that lets us identify what happens when we upscale without having to go down this dangerous road of mathematical ingenuity. So, at that point, I'll open the floor up for questions.
Thanks for the very stimulating talk. So we have some time for questions.
So if I understand you correctly, you're advocating for a strong emergent approach. Most of the other scientific disciplines have benefited from weak emergence and following that approach. Why do you think hydrology is different? Could you comment on that?
I don't necessarily. I'm advocating for this approach because I think that, that there's some utility in it, and I don't think you can go either way. You can go from top down, or you can go from bottom up. Both approaches may give us useful answers. The important thing, of course, is the journey, right? So, is trying to look at this question of upscaling is the most useful thing. How we get there, I think that there's more than one way, and I'm just spelling out two of these here. So I don't have a strong opinion upon how we get there, other than we have to recognize that some of the more theoretically rigorous approaches are taking us down a dangerous path that's not particularly useful.
So then just as a follow-up to that, then, do you worry that there's a strong possibility of false emergence coming out of these upscaling? Because and I mean, you kind of alluded to this at the start, where if you have these large upscaling parameterizations that reduce back down to their microscale, so that would implicitly assume that the weak emergence approach is sound, then there's a possibility of a strong emergence creating a false.
I think that you can definitely get a false emergence that may be only valid under a few conditions, which you may not be fully aware of what those conditions are. I still think that's better than ignoring it all entirely and either going with the brute force approach or trying to use the non-upscaled equations in order to solve the same problem, which I think that's a much more dangerous approach than to recognize the fact that we need to respect that the rules at the larger scale are not the same as the rules at the smaller scale. So even if there's false emergence there, I think you're still leaning on the side of getting it right versus on the side of getting it wrong.
Other questions?
So upscaling, you've shown that it doesn't hurt hydrograph response. So we can repeat hydrograph by upscaling. But you will lose many good information on tracer response, on water quality response. So do you see any future on upscaling that respect tracer response?
Yeah, I mean, I think that still is also so that's a more complicated system, and it will. It is not as simple in terms of its emergent behavior. So for tracer response, you're going to have to characterize a lot more detail of the system. To characterize travel times and transit times in the subsurface, you need to actually have a very good handle upon distribution of flow paths and whatnot. So that one will be less amenable, I think, in general to upscaling. The transport problem is a much nastier problem to solve.
So solving hydrology is enough?
In
today's research?
No, I'm not saying that at all. I'm saying that I'm advocating for recognizing that upscaling is an important issue. I'm not advocating that there's any specific means by which to do it. I am also advocating for the fact that we can't use the point scale relationships and just assume that they're correct. But yes, there's going to be some systems, as I said here, that can't be upscaled, and I think there's a lot of transport problems which you may just not be able to do it. And in fact, that's been demonstrated. So there's some really neat work by Daniel Tartakovsky, which basically he does this hybrid multi-scale modeling where they model at the large scale and the micro scale, and they go through the full spectrum and they can demonstrate certain conditions and certain types of systems where you need to know the microscale in order for the macroscale to work at all. And so some problems are not going to be solvable unless you know and can represent the microscale detail, and those you're going to have to use some of these multi-scale modeling approaches, and there's a whole literature in continuum mechanics for that. I think in hydrologic systems, you're looking at water quantity, I think there's a lot of opportunities to avoid the microscale because naturally the systems avoid the microscale. I don't know any better way to say that.
So I have a quick question, and then Kevin has also one. So I really enjoyed your talk and the discussion. Just back to fundamentals and definitions, I was a bit confused at the beginning. So basically, you're falsifying the idea of having a conceptual parameter, right? Let me finish this.
Okay, sorry.
Yeah. So and basically, to explain that, you use that plot that you map the distribution of parameters to the model state values or outputs, and you were basically saying that the expected value of the input wouldn't map to the expected value of the output.
That's correct.
So by that definition, I got the impression that you mean the conceptual parameter is the expected value of the distribution of model inputs. But my impression is that the conceptual parameter is our best guess to generate the expected value of model outcome. So we don't really look at the distribution of parameters to come up with the expected value, or to come up with the conceptual parameter.
We might have to take this elsewhere because I'm not sure if I entirely get your. So there's two things. There's the talk. I was discussing the use of effective parameter models using.
Sorry, effective parameter.
Yeah. So that's different. So the effective parameter. This is the dangers of what I'm talking about. So for example, you can't directly apply the Darcy-Buckingham law on a heterogeneous surface to determine the average flux through a plane that's heterogeneous and use even an effective saturated hydraulic conductivity. And definitely not an effective soil characteristic curve. We can't just directly assume that relation is valid over a larger scale.
Okay, I think I get your point on that, but this is something for further discussion later. We can follow that up.
Just a quick question, I really like that you talked about the difference between linear and nonlinear processes. I thought that was really important. One question though, dealing with the not just the effective variability in parameters or states, but what about forcings? What about the effect of dealing with the complex multi-scaling variability of forcings in space-time? How is that going to interact with nonlinear processes?
It's definitely going to play a role, and I'm not. And so again, I don't profess to have solved these problems, and I'm not even sure if that's necessarily a solvable problem. But I think that we start small. We start looking at the simpler processes, which we may be able to get away with appropriate upscaling. And then we add complexity, and we might never get to the point where we'll be able to upscale with heterogeneous forcings and heterogeneous landscape. But trying to understand how those systems will scale up is still a valuable process.
Just an observation that a linear model, like a unit hydrograph, can do it.
Yep.
Okay, I think this is a good point to close the session. Thanks very much, James, for coming. So, yeah.
I know.